My name is Samantha Aziz, and I am a doctoral candidate in computer science at Texas State University. Today, we'll be discussing how the recent convergence of eye tracking and virtual reality has introduced some new user privacy considerations. And we propose this work to motivate future research that addresses these two technologies comprehensively. Now, the motivation for this work is rather simple. Virtual reality platforms collect a lot of user-generated data. These platforms generally have sensors that can track the user's body, their gestures, their gait, their speech. And this sensor data can reveal physical characteristics that can be used to identify a user. In more recent VR platforms, we're also seeing the growing integration of eye tracking functionality. Eye tracking fulfills some important roles like foveated rendering and cyber sickness mitigation, but eye tracking data also reveals personal characteristics about a user that are often cognitive in nature and can even be used to uniquely identify users outright. So we have two types of data being collected synchronously, both of which can be misused to identify users, and both of which convey different kinds of personal information. Now, this presents a new problem for user privacy in virtual reality platforms. Namely, the problem is that the simultaneous availability of these two data streams might introduce a significant combined risk for user identification. Current methods for obfuscating sensitive information from these data streams are effective, but they are typically developed for just eye tracking or just VR data in mind. They don't generally consider that more than one vulnerable data stream is available at one time. And as a result, we have a limited understanding of how these privacy mechanisms perform when eye tracking and VR motion tracking are available on the same platform at the same time. So our goal today is to characterize the risk of unauthorized user identification in this context. In this work, we present a case study simulating an adversarial privacy attack that leverages current gaps in the research to perform unauthorized user re-identification. In our simulated attack, we consider an adversary who attempts to identify users using body and motion and gaze data collected by a VR device. We are really interested in stress testing the privacy mechanisms that are applied to the user-generated data. We explore whether this adversary would be able to successfully perform user identification when none of the data streams have been privatized, when all of the data streams have been privatized, and when some, but not all, data streams have been privatized. We're particularly interested in this partial privatization scenario because we want to know whether the personal information encoded in this unprivatized data can bypass the privacy protections applied to other streams, thereby enabling user identification. To actually simulate this scenario, we utilized a few publicly available datasets and models from the literature. First, we used a subset of the Open Needs dataset, which contains motion data from eye trackers, a VR headset, and two Oculus controllers. To identify users, we utilize a state-of-the-art biometrics model from Lohr et al. Called I Know You 2. We train and evaluate I Know You 2 using four-fold cross-validation with splits occurring by subject number. We report biometric performance as the rank 1 identification rate across all four folds. And in the full paper, we also assess biometric verification rates. Those results are available in the full work. We train 20 different models, each using data that has varying degrees of privacy protection applied. To impart privacy protection, we use two state-of-the-art privacy mechanisms for user-generated data. For body motion data, we re-implement a portion of MetaGuard from Nair et al., which adds bounded noise to the height component of the headset and the positions of the controllers. And for eye tracking data, we apply a methodology from Wilson et al. That obfuscates identifying information by linearly smoothing raw gaze signals. Now, we want to use this case study to highlight four key insights that warrant additional investigation in future work. So, we first establish a baseline for identification performance when using unmodified data. As you can see in the results to the right, the identification rates are pretty high, even for single stream test conditions. They're all certainly above chance level. So even if some data streams are more informative than others, we have insight number one here, both gaze data and VR motion data are indeed suitable for user identification in this problem setting. When we additionally provide two or more data streams for user identification, we start to see that identification rates generally increase relative to using any single source alone, with our highest identification rate of 75% occurring when we provide all data streams. This suggests that our model can recognize unique behavior more effectively when it is captured simultaneously in all three data sources. And this brings us to a very important point for our work, insight number two, that combining complementary data increases identification rates over our single source settings. So these insights validate our privacy concerns and give us a baseline of biometric performance for this case study. Our next step is to explore the effect of privatizing data on the observed identification rate. So on the chart on the right here, results in red are experiments where no data has been privatized, and results in blue are experiments where all available data streams are privatized. Generally, each privacy mechanism is effective at reducing identification rates compared to the unmodified data, indicating that users are harder to distinguish from one another, which is good for user privacy. Now, when we combine privatized data streams in experiments 11 through 14, you'll notice that the effectiveness of the combined privacy mechanisms depends on the quality of protection afforded to each individual stream. This leads us to another insight, number three. In a platform with multiple data streams, privacy enhancement is only as strong as its weakest link. This leads us to our fourth and final insight. We observe that the presence of at least one raw data stream can increase identification rates relative to fully privatized settings. But the exact privacy risks are difficult to predict without formal analysis and may vary on the specific implementation techniques used in one particular environment. In the scenario on this slide, we have both gaze data and VR motion data available. We know from our previous experiments that when this data is fully privatized, we get identification rates of 40%. But when data is not privatized at all, we get identification rates of 75%. We conduct two experiments where we provide I-know-you2 with various combinations of partially privatized data. In experiment 17, when only gaze data is privatized, we see a very high identification rate of 72.5%. This identification rate is so high that it appears as though no privacy mechanism has been applied at all. The biometric model was able to use the raw VR motion data to completely circumvent the privatized gaze data, which validates the concerns that originally motivated this paper. In experiment 20, where we only privatize VR motion data, you'll see that experiment 20 only produces an identification rate of 48%, which is similar to our fully privatized setting. We suspect that this happened because there's a much higher volume of privatized data than unprivatized data in this experiment. Our gaze data only represents two channels of inputs, and the XR motion data represents a full 9 channels of input that were privatized beforehand. Because the majority of the overall data was not informative for biometrics, it was likely harder for the biometric model to correctly identify user-specific behavior. So, despite the privacy leakage from the gaze data, the fact that the privatized data accounted for a majority of the overall input means that we have less observed impact on user privacy than we might expect. This does not mean, however, that the users in experiment 20 are necessarily more protected than users in experiment 17, because these results will absolutely depend on the details of whatever technique is being used to perform the identification attack. Great. So to wrap up, I would like to briefly discuss where this research should probably head next. First, I want to emphasize to you that a comprehensive privacy solution for VR should involve multiple layers of privacy protection so that there's no single point of failure that might enable privacy violations. But to advance this specific line of research, it would be worth formally investigating how much complementary information these user-generated data streams contain, and whether specialized techniques like sensor fusion could more effectively extract this complementary information for nefarious purposes. We can then build on this work by improving the explainability of our results through explainable AI techniques to help us apply more principled, generalizable analyses of privacy risk in this context. And finally, we can continue to pursue privacy mechanisms that can provide formal guarantees of privacy for physiological data, or otherwise implement methods to certify privacy at runtime to advance more consistent privacy guarantees.